So hello everyone and welcome to this fourth week of the course of networks. And today what we're going to be talking about is the concept of community detection. So what is that? What is community detection? Well, we've seen in the last few weeks that there exist different ways to measure different aspects of graphs and networks. So for instance, we've seen that the local cohesion of graphs can be measured by the so-called clustering coefficient. We've seen that motifs and the importance of certain motifs can be captured by comparing the frequency of motifs in a graph with those that would be observed in a randomized node model. We've talked about the degree distribution, which is a way to characterize the diversity, the heterogeneity that is present in a graph. But today what we will be considering is something quite different. We'll try to characterize how a graph is organized into different clusters or modules. So it means that instead of seeing a graph as one big connected entity, we'll be trying to characterize its organization into groups. For instance, this blue group, this black group, this red group, and so on and so forth, defined in such a way that most of the edges will be inside the groups, and there will just be a few connections between nodes of different groups. Now, something quite important is that actually many graphs from many disciplines tend to be organized in a modular way. And that would be the case, for instance, of this example, that is a social network where the nodes would be individuals and the links would represent social interactions. Here, you would basically have some information network about the connections existing between papers published in different disciplines. And here, there would be some biological network. I think it's a protein-protein interaction network. And in each of those cases, well, actually, different algorithms have shown and shown again that the graphs are not homogeneous, but are made of these components that are dense and weakly connected with each other. Now, not only did people show that graphs are modular, but also that they are multi-level modular. So they are hierarchical. And here it means that a graph would be composed of modules, but the modules themselves will be organized into submodules, also organized into sub-submodules, and so on and so forth. So you need to think of some sort of like a Russian doll organization where the graph is composed of groups that will be present at different scales inside the system. Now, before we go further, well, this type of organization is usually called hierarchical or multi-level modular. But the thing is that in graph theory, hierarchies have different meanings. And I just wanted to clarify that the hierarchies that we are talking about now are quite different from those that would be associated to some subordinate relations. For instance, in an army where you would have a general who's above the colonels who are above the captains, above the sergeant, where you would have this kind of flow from the important to the less important nodes. But this is obviously something that is called a hierarchy, but it's a different hierarchy than the one that I'm interested in here to the left. Also, if you search into the literature, you will see that some authors have been basically proposing some sort of like a measure of hierarchy that is based on some self-similar organization, some sort of fractal type of organization that might be present in graphs. And they decided to characterize this by looking at the relation between the clustering coefficient and the degree of the nodes. So this is clearly some interesting work with interesting observations. But again, it would be a notion of hierarchy that is very different from the one that we'd be interested in. Now, the thing is that very often when you have certain properties in mind, you also come with some random graph models that allow you to play with these structures and to generate ensembles of random graphs that have some desirable properties. And this is clearly the case for networks with communities. And indeed, there have been plenty of methods and models that have been proposed in order to generate graphs, like ensembles of random graphs, having certain modular structure that can basically be modulated and controlled by the user. So one of the applications of these types of models is actually for the validation of techniques, where you have some method that aims at finding clusters. Well, you test it on these instances of a random graph model with communities, and the goal is actually to find back the communities that you've been planting yourself. Now, actually, these random network with communities are very much connected to the ADOS-RNE graph that we've been seeing last week. Now, in the ADOS-RNE graph, if you remember, we had just one parameter, P, that would be, or Q, that would be the probability that any pair of nodes would be connected, and all of these would be independent Bernoulli processes. Now, when you go into random graph model with communities, with clusters, well, typically the way you do is to consider something called stochastic block models. And in stochastic block models, instead of having one type of node, you define that the graph is made of C communities. And in the example that I just plotted, the C would be equal to 3. And what you do is, so you assign each node to a certain community, and then you define a certain affinity matrix that tells you what is the probability that a node of community Ci is connected to a node of community Cj. And actually, clearly, well, if you define different probabilities for different types of relations, well, you will basically produce graphs that may either have some community structure, like here, if you put most of the weight on the diagonal, meaning that nodes from the same groups are more connected than nodes from different groups. But you can also have other types of something usually called generalized communities, where in this case, you would have that there are many connections in the group number 1, many connections between group number 1 and group number 2, many connections inside group number 3. And this leads to some complex organization that can still be characterized into a structure of blocks. Blocks in the sense that your adjacency matrix is organized into different types of blocks. Now, stochastic block models have gained a lot of popularity in recent years, and they've actually been used as a way to uncover communities in unknown networks. And typically the way to do is to take a graph, an empirical graph, and basically to try to find what would be the stochastic block model that is the most likely to have generated the data that I observe. This can be done by maximizing a likelihood function. And this is one way, amongst other ways, to try to find groups of nodes here from a modeling perspective. Now, we will not go too much into the details of these stochastic models, and instead we'll be looking at other families of methods that exist and that try to find communities in empirical networks. So, well, this is actually the problem. What is community detection? Well, in community detection, what we try to do is to start from a graph and to have an algorithm that will be able to find the groups of nodes that are present in the graph in an automatic fashion. Now, ideally, you would like to have a method where you don't need to impose how many groups are present or what is the size of the groups. You would like to have a method that automatically takes the graph and finds the groups of nodes that are composing this graph. Now, why is that an interesting problem? Well, there are many reasons for that. And the first very good reason is the fact that graphs are very often used for visualization purposes. Very often when you have a system, you can plot that graph in 2 dimensions. But the problem is that you have initially a graph that is a high dimensional object. And if you plot it in 2 dimensions, you embed it. And clearly some choices will need to be made in order to optimize somehow your visualization. Now, the visualization of graphs in 2 dimensions typically works well for small graphs up to a few dozens of nodes. And this would be the case here to the left, where what you have is a social network where the nodes are students of a school and the links represent some intimate relations that these students have had together during a year, and where after plotting it, you directly see that the graph is a very complex organization where, for instance, there is the existence of a large connected component, which means that some sexually transmittable disease would have had the occasion to infect a large part of the cohort of students through indirect connections. Now, unfortunately, if you have a graph that is larger, and that starts usually with a few hundreds of nodes, typically what you'll see is just a blur, just a bowl of nodes that is completely meaningless and uninformative. Now, one way to deal with this situation is actually to resort to community detection. And the communities will be seen as a way somehow to change the resolution at which you try to represent your graph. And indeed, if instead of trying to represent the whole graph, you first find the communities and then represent the network at the level of the communities, well, that's a way to reduce the number of nodes to represent, to change, to cold grain the way by which you do your representation, and a way to improve the legibility of the graph itself. Now, actually, this is a type of method that is implemented, and this is an example from a company of some colleagues called Infobaline, where they've been proposing a way to navigate and to represent the whole network of Wikipedia. So Wikipedia would be a network where the nodes are the pages, and you have hyperlinks between the different pages. And clearly, this is a huge graph, very complex, very much interrelated. And the way they did was to propose a way by which you can look for clusters, and that would be a cluster here, where you would only show what are the important nodes based on the notion of centrality, and the important one would be here, big data. And you would see that there are connections between some clusters with other clusters. And so you can navigate and see the connections between the clusters. But you can also either zoom in or zoom out, by thereby looking for larger communities or smaller communities and changing the resolution at which you are exploring the graph. Now, just for the fun of it, if you're a researcher in applied math, well, one more reason to study community detection is that actually there is a very, well, not prestigious, but prize, that there's a prize that can be won that is associated to the study of the Karate Club, which is a social graph that we've been talking about before. And if you do an original analysis of the Karate Club at a conference, and that the owner of the Karate Club trophy is present, you will be the person who receives it next. And so it means that this trophy, this small trophy, has been doing some sort of a random walk between researchers doing community detection. And well, I continue to talk about it because I've never had it. Otherwise, I would be in the photograph here. And clearly, one of the big achievements that I want to reach in the next few months is to get hold of this small trophy. Okay, so now, what is a good community? Well, actually, and as we'll discuss, there is no one single definition of what a good community is. So obviously, if a graph is made of different connected components, we expect that the communities should not be spread across different components. It seems to be like at least a basic requirement. But for the rest, the way to divide connected components into small groups is a task that can be defined in different ways and reach different solutions. Now, actually, the problem of community detection, even if it's a fairly new problem in the sense that it emerged maybe 15, 20 years ago, but it's very much connected to an older problem from graph theory called network partitioning. And these are two problems that are somehow related, even if they are quite different in their practicalities and in the solutions that they provide. So in graph partitioning, what you try to do is to basically to partition a graph into a certain number of groups where a user determines how many groups there are and typically what are the size of those groups. So a good example would be the bisection problem, where you try to find what is the best division of a graph into two groups of equal size. Yeah. Now, what would be the kind of applications of this kind of problem? Well, this is it finds applications in circuits, for instance, design, and in order to minimize, for instance, inter-processor communication. Yeah, You try to minimize the number of exchanges that exist between different parts of your graph. Then community detection, you proceed you have a very different question in mind. What you want to do is to find what is the best way to divide the graph into groups without imposing the number or the size of the groups. You would like to have a method that by itself finds these numbers and these sizes. But even if the problems are different, they tend to rely on relatively similar methods. And typically in both cases, the way to proceed is first to formalize the problem by providing a mathematical definition of what a good community is. And then you need to find some practical ways to solve that problem, which typically requires some optimization techniques. And the thing is that these optimization techniques from network partitioning can somehow be generalized to the case of community detection. So to start, well, let's look at this graph bipartition problem, which is a graph partitioning problem. And let's assume that the problem that you need to solve is the following. You want to find what is the best division of a network into two groups of size N1 and N2, such that you're going to be minimizing the cut size. And what is the cut size? Well, the cut size, let's say that I have a graph like this, and that my two groups are this one here and that one there. The cut size is the number of edges that go from nodes of one group to nodes of the other group. And so here the cut size would be 1. And so what you want to do is to have a graph and to find the best way to divide them into two groups of size N1 and N2 in such a way that you minimize that cut size. Obviously, well, you could try to proceed very naively and try to solve this problem by looking at all of the possible bipartitions of size N1 and N2. But unfortunately, this wouldn't be possible because the number of ways to divide a graph made of two nodes into two groups explodes with the total number of nodes. And typically, if N1 is equal to N2 is equal to a certain N, and you have a graph made of two N nodes, you will basically have the number of partitions of two N nodes into two groups of N nodes is going to be growing exponentially. So it means that typically you will need some heuristics in order to find some approximate solutions of this problem in non-prohibitive times and to deal with, graphs that are not too small, and typically in graph that would be large, made of thousands or tens of thousands of nodes. Now, one way to address this problem is actually to consider some relaxations of the optimization problem. The optimization is to minimize the cut. And one way to do these relaxations is to adopt some spectral methods. So how do you do so? Well, the cut, by definition, is given by this expression here. So it's 1/2 of the sum for all pairs of nodes in different groups of the adjacency matrix. Now, what we'll do is we're going to be encoding the group to which the node belong by a certain spin, like where that could be either +1 or -1. And if we do so, actually, and I think it should be a 4, you can directly rewrite that your cuts can be rewritten in terms of a matrix Lij that is called the Laplacian of the graph. And what is this matrix Lij? Lij, it's equal to Ki delta Ij. So you put the degrees on the diagonal, so minus degrees plus Aij. So what you have is you have your adjacency matrix, and you basically have minus the degree that you put on the diagonal. Now, if, wait, let me just check that I didn't say anything wrong. So some, no, actually it's going to be plus here, sorry, and a minus here. Now, the Laplacian is a matrix that we're going to be seeing quite a few times in this course. And we'll see that it's directly related to the Laplacian that you know from continuous differential equations and the heat equation, for instance. And we'll see that the Laplacian naturally appears for many families of diffusive processes that take place on graphs. Now, the most important for now is the fact that actually the Laplacian is a positive definite matrix that is such that all of its eigenvalues are, so we have 0, smaller or equal to lambda 1, smaller or equal to lambda 2, and so on to lambda n. Now, what we have is that actually the lambda 2 will be different from 0 if you have a connected graph. And otherwise, the degeneracy of the 0 eigenvalue of your Laplacian will give you the number of connected components of your graph. So here we'll be assuming that the graph is connected. The lambda 2 is going to be larger than 0. And clearly, if you look at the expression that you have above here, what would be the way to minimize the cut in a non-trivial way? Well, of course, the lambda 1 contributes 0. So what you want to do is to choose basically a vector S that would be the eigenvector associated to the lambda 2. And if you do so, you find an optimal value, a minimal value for your cut that would be 1/4 of this lambda 2, that is the smallest non-zero eigenvalue of your Laplacian. Now, well, it seems like we solved the problem. What is the solution of the optimization? We need to take that the S is actually the eigenvector associated to the lambda 2. And this eigenvector is usually called the Fiedler vector. Now, actually, well, when you think about it, it looks like we solved it, but we didn't solve it. And why is that so? Because the vector S that we defined had a very constrained organization. It can only be made of +1s and -1s. While the vector S that we have here, it's a vector that comes from the graph. It's this dominant eigenvector, and we cannot be sure that it has the right organization. So it means that if you now want to find what is the right vector S that minimizes the cut, well, what you need to do is to try to find a vector S that is as close as possible to this dominant eigenvector. And typically the way to do so is the following. So let's assume that here are the entries of my eigenvector, of my Fiedler vector. And let's assume that I want to divide my graph into two groups, one of size 4 and the other one of size 15. Yeah. Well, what I'm going to be doing is to try to find a piecewise constant vector with 4 nodes and 15 nodes that will be as close as possible to this Fiedler vector. And so if I am to plot the entries of my Fiedler vector, well, I will have some positive entries if I order them from the most important to the less important and negative ones, right? What I would like to do is to find a group of 4 and a group of 15 that will be as close as possible to this Fiedler vector. And the way to do is actually to take the 4 highest values in one group and the other 15 in the other group. So N1 in one group, N2 in the other group. Then to take the N1 most first ones in the first group and the others in the other group. So we take 4 and 15 or 15 and 4. We look at the two possibilities basically to define this piecewise vector. These two are defining for us a partition. We have 2 partitions. And what we simply need to do now is to select the partition that is such that its cut will be as small as possible. And so it means here that what we do is we initially have a problem. We then relax the problem, finding the exact solution to the relaxed problem. The exact solution is that we need to take a vector that is this Fiedler vector. And then we go back to the original problem associated to a bipartition, by finding the bipartition whose vector is as close as possible to the Fiedler vector obtained as the second dominant eigenvector of the Laplacian of the graph. So, well, this is a type of method that is quite general and that can be used actually in different contexts. Now, this concludes this first video, and now in the next video that is going to be following in a few moments, we'll be looking now at the community detection problem, and we'll see that actually some similar ideas can be used in order to find the best way to partition a graph into communities in a very efficient way. So hello everyone, and welcome for this second video of the week, where, if you remember, so the main topic of this week is community detection, this problem of finding clusters, of finding modules in large graphs. And what we've seen in the first video was how this problem relates to the problem of graph partitioning. But what we're going to be doing today is to look at community detection itself, which is, as we'll see, slightly different. So the main difference between graph partitioning and community detection is the fact that when you are focusing on community detection, you don't want to impose the number of clusters of your optimal partition. You would like the method to find by itself what is the right number of modules, clusters, and what are their sizes, depending on the underlying structure. And to do so, typically one way to proceed is to define a quality function that allows you to compare partitions made of different numbers of modules. So that would be a number, it would be a function of the partition of a graph. That would be such that, for instance, for this partition, it would give it a certain value Q1, that one Q2, that one Q3, and so on. And if you can find such a quality function, then you can compare partitions of different types, and then you can search among all of the partitions of a graph what would be the best one for that specific quality function. Now, there have been quite a few quality functions that have been defined for this purpose, but the most popular one is, without hesitation, a quantity called Newman-Girvan modularity. And Newman-Girvan modularity is defined as follows. It's defined as the fraction of edges within communities, the communities of the partition, that you compare with the expected fraction of such edges in an appropriate null model. And the choice of this null model, as you see, is an additional choice that you need to make. So, well, two things to say. Well, first of all, in contrast with graph partitioning, where we were trying to minimize the number of links between the communities, here we are trying to maximize the link inside the communities. Yes? It really feels like a clustering problem. The second thing is, well, let's have a look at what this definition, this general definition, looks like mathematically. Well, the standard expression for community detection is the following. So for each node I, we will assign it a certain community Ci, and then we will define what is the quality of that partition encoded by the Ci's as Q, which is the standard letter for Newman-Girvan modularity, given by 1/2m, where this is the number of edges, and it's just used in order to, well, just as a normalization. And then you do a sum over all pairs of nodes that are such that Ci is equal to Cj. So we just sum pairs of nodes that are inside the same communities. And we add two terms, a positive one and a negative one. The positive one simply counts the number of edges inside the communities. The second one is a negative term, and you subtract what is the expected number of such edges inside the communities in an appropriate null model. Now, the standard choice for this null model, Pij, is to take Ki times Kj over 2m. And if you remember, that's exactly the expression that you obtain for the configuration model that actually gives what is the expected number of links between a node I and a node j, if everything was to be random except for the fact that these nodes have specific degrees. Now, when you think about it, this expression Pij will tend to be large in situations when the degrees of the nodes are large, and it's going to be small otherwise. Which means that you penalize here, in this quality function, the fact of putting nodes with high degrees together. You try basically to put these nodes with high degrees in different communities by this choice of a null model. And for this specific choice, so we have the standard expression for Newman-Girvan modularity, because indeed this null model is used in at least 99% of the applications. And you obtain this expression where you have indeed this Ki kj over 2m that appears here. Now this Quality function can be shown to be a number between -1/2 and 1. And most importantly, it allows to compare partitions made of different numbers of modules, which is what we are looking for. Now, just a small note on the choice of the null model. So here we've been using a null model that is based on constraints on the degrees of the nodes and associated to the configuration model, but actually other choices could be made. And for instance, in situations where you have a directed network, you may want to impose constraints on the in and out degrees on all of the nodes. The standard choice would be this one that would be associated to the directed configuration model. But there are other choices that are possible. For instance, situations where you don't care about the degrees, you could simply use a constant. That would be a constant probability. That would be some sort of like assuming that the graph is compared with another Schrödinger graph, basically. But otherwise, you can also have situations where the graph is embedded in space. The nodes have location in space, geographical space, for instance. And then what you may want to do is to detrend for the influence that space has on the likelihood to have a connection between nodes. And that can be done by incorporating a certain function that depends on the distance of the nodes inside the space that you use as your null model. But in all of these choices, a basic requirement is to assume that the total number of edges or the total weight of all of the edges inside the graph and inside the null model need to be the same. And that is always the same number. Okay, so actually modularity can be shown to have a certain number of properties. And one such property is the fact that if you take a partition made of one single module, you will have that the partition of that partition made of one single module is equal to 0. So this implies that if you were to find a partition that has a positive value of modularity, that will be better than putting all of the nodes together. Now, a second property that is quite interesting is that actually it's not so difficult to show, and I'll leave you these notes to have a look at the details. It's not too difficult to show that if you were to have a partition where one community is disconnected, is made of two groups of nodes that are not connected with each other. And so, for instance, you would have something like this, right? You have this, and then the rest of the graph. But what you have is that you've been putting these nodes together, and even if they don't have direct connections with each other, well, then it is always better to separate this group into two subgroups in order to ensure that each of the communities would be connected, which is again a very intuitive, I think, property that implies that the optimal partition of modularity needs to be composed of connected communities, which very much makes sense. Now, okay, so we have now a quality function, this Newman-governed modularity. Now, the problem is that it's been shown that the optimization of modularity is an NP-complete problem, so we need some efficient heuristics in order to optimize it. Now, there are typically two families of methods that people use. And the first one is actually a direct generalization of the spectral methods that we've been presenting in the case of graph partitioning. So here is how it works. So here, if you remember, for graph partitioning, we naturally had a Laplacian matrix appearing. But here actually we'll be focusing on the matrix that is called the modularity matrix, which is this matrix that appears simply in the expression here for modularity. Now, given that matrix, well, what we're going to be doing is to encode the belonging of nodes to communities. And here, the first step is to try to find what is the best division of the network into two communities. And if you can find this best division into two communities, then you can reiterate this process iteratively in order to find smaller communities by always dividing the communities into two in some sort of a binary tree. Now, because you look for two communities, you can encode these communities by just +1, -1. And what we're going to do is to exploit the fact that delta Ci Cj that should be equal to 0 if the communities are different and 1 if the communities are the same, is actually directly expressed by this expression of Si and Sj. And from there, we have that modularity can be rewritten as a bilinear product where you have the Si and Sj's that appear. It looks very much like what you had before. The main difference with the Laplacian is that the Laplacian was a positive definite matrix, and that all of its eigenvalues would be positive except for the one associated to 0. Well, in the case of the modularity matrix, that's not the case. That's a matrix that can have positive or negative entries. And here, well, typically what we're going to be doing is to use a spectral decomposition of that matrix, that is a symmetric matrix. And now, if we want to maximize modularity, what we'll do is to choose a Si that will look like the Vni, the eigenvector whose eigenvalue is the largest. We want to try to find a vector that is as close as possible to the eigenvalue with maximal to the eigenvector with maximal eigenvalue in order to ensure that this quantity will be maximized. And so how would we do so? Well, the standard trick is simply to say that, well, anytime you have a positive entry for the eigenvector, you put Si to be equal to 1. Every time you have a negative entry for the eigenvector, you would put a -1. So if I rearrange my nodes label, and if these are the entries that have been ordered from the largest to the smallest, what I'm going to do is to choose a Si that would be something like this, right? Where those nodes with positive entries are in community +1, for instance, and those nodes with a negative entry would be in community -1. Okay. And this is indeed a method that can be repeated iteratively in order to find what would be the optimal partition of a graph. Now, spectral methods have revealed to be very efficient in practice, except for the fact that, well, they can be slow and can be computationally hard to implement for graphs that would be larger than a few thousand of nodes. So typically, people use those for small graphs, but as soon as the graph becomes larger, then actually they rely on other sets of techniques, and those would be greedy optimization techniques. So here, what I would like to do is to present one such technique, which is called the Louvain method. And I present it, well, for two reasons. Well, first of all, I was one of the authors of the method, which means that I know it quite well. It's kind of going to be easier for me to explain it. But more seriously, I'm going to present that method because it's a de facto standard these days when you optimize modularity, because the method has been implemented in most libraries and in most programs for the analysis of graphs. So how does the method work? So the method works by proceeding in a greedy fashion. So initially, you give an order to the node. And so you simply say, well, there is a node number 0, 1, 2, 3, and so on until n-1. And then you see that initially each node belongs to its own community. So node 0 is in the community 0, and so on and so forth. So initially you have n nodes and n small communities of single nodes. Then what you do is, well, you start from node 0, and you try to take it out of its community and to put it into the community of one of its neighbors. And you do that for all of the neighbors. And if there is an improvement, you do the move where the improvement is best, is largest. And so in this case, you would be putting node 0 in the community of node 3. Then you do this step for node 1, 2, 3, and so on until n-1. And at n-1, you go back to 0, 1, 2, 3, n-1, and you continue until nothing happens. And when nothing happens, at the end, you arrive at a partition, at a configuration that would be this one here, where in this example, we have 4 communities, and we cannot improve this anymore by these local moves. So we reached a local maximum of modularity, basically. Then actually the next step now will be, okay, because we reached the local maximum, can we maybe somehow change the rules by which we move the nodes in order to try to escape this local maximum? And the way to do is going to be to change the scale, and instead of doing local moves, we're going to be now moving groups of nodes at larger distances. And the way to do so is to have a second phase to the algorithm. The first phase was this local optimization. The second phase that consists in changing the level of representation of the graph. And in this case, in defining new nodes that would be the communities of the original graph. Yeah? And so you started from a network, you build a smaller network with less nodes, where the nodes are the communities that you found in the first phase. And where here you need to keep track of what were actually the connections between the nodes in the original graph by defining some weights between these new nodes. And so, for instance, between the green and the blue nodes, we have 1, 2, 3, 4 connections. Well, this means that we will have to define a weight of 4 between the green and the blue community to ensure that we preserve the structure when we change this, when we coarse grain basically the representation of the system. And well, now, actually, something important to note is that the number of nodes is going to diminish drastically during that step. And now what you do is you proceed iteratively. And so what we'll say is that we are going to be we define a path to be a combination of these two phases. And so after the first one, we arrive at a smaller network of communities. And then again, we're going to be trying to do some local optimization on this one, and then we do another coarse grading, and we continue until no improvement of modularity is observed. So this is just another example, and I apologize, it's in French, where we see that we start from a graph where we have n communities, we do a local optimization, we do the coarse grading, and when we do the coarse grading, we obtain 4 communities that are the blue, the light blue, the yellow, and the orange. We do optimization again, we do coarse grading again, and we arrive there at a configuration where if we try again to do some local optimization, we don't observe any improvement anymore. And that basically means that the algorithm reached its maximum. We cannot improve modularity anymore by this sequence of 2 types of steps. And hence, we stop the algorithm. And here you see that we started from a modularity of 0.08 initially. And we've been reaching at the very end a modularity that is a modularity of 0.45. So indeed, we've been increasing modularity along the steps. Now, okay, so there are some interesting properties for this algorithm. Well, the first thing is that we've been trying to show what was the complexity of it, but actually its complexity was not so good, and actually it's not so it's not so surprising. Why? Because actually the network is exploiting the structure that may be present in the graph, and when there is structure, it's going to be very fast, as we'll see in a second. But on the other hand, if you have a graph that is very random, for instance, like a stochastic block model, for instance, where there is no structure to exploit, where there are not these structures at different scales that may be present, well, actually, then the algorithm is much smaller. So it means that it tends to be very efficient for real-life networks where we have some structures to exploit. And part of the efficiency of the algorithm comes from the fact that every time you need to you estimate the move of taking a node out of its community and moving it to the community of one of its neighbors, this move only requires some local calculations. So it only requires calculations when you estimate properties of the node and its neighbors, and nothing more than that. Which means that even if you have to do this step many times, because we have many times to take a node of its community and to move it to neighbors, these steps are local and can be done in order 1 as an order 1 calculation. Now, okay, so at the time, when we presented that method, we had to try to convince the community that it was indeed a good solution. And this is a table that comes from this original paper that is more than 10 years old now, where what we did was to compare the result of our algorithm with what was at the time the state of the art. And the validation that we did was to compare, to look at graphs of different types. So we have the Karate Club that we've been talking about before, the Archive Network that is a network of communities, of collaboration between scientists. We have the Internet, part of the web, a mobile phone network, other parts of the web. And we have graphs of different types, but also graphs of very different sizes. So we go from 32 nodes to 118 million nodes, and we go from 77 edges to of the order of 1 billion edges. And what we did then was to compare two things for each of the methods. On the left, we have the value of modularity that is observed when doing your optimization. And on the right, you have the time that it took on the same computer to run the algorithms and to reach the maximum. And as soon as the calculations took more than 1 day, I think, we didn't show the results. We assumed it didn't converge. And what you can see here is that in all of these situations, well, actually you will see that this Louvain algorithm always provided high values of modularity. For instance, you can see it here, right? But also the time that was required for the calculations was drastically smaller. Here you had a change of the order of 7 or like 800 with CNN. That was the method that most of the people used at the time. And because of this velocity, we could go to graphs that were much, much, much larger, up to, in this case, of the order of 100 million nodes and 1 billion edges. And actually, the only limitation that we had was not really the time itself, because here it ran in just 2 hours. It was more that, 10 years ago, we had some RAM issues. We needed to store the graph in rapid memory. And this was basically the largest graph that we could store in rapid memory. Now, okay, so more generally, so what are the methods that people use in order to compare different methods? Because here I've been presenting 2 ways to optimize modularity, but actually there are hundreds of ways that people have been proposing to optimize modularity, some good, some not so good. But there are also methods that are based on other quality functions. So there's, for instance, a quantity called the map equation, where instead of optimizing modularity, you optimize this quantity that is the map equation that tells you from completely different principles here based on coding theory whether or not a partition is good. Well, when you try to compare methods that optimize modularity, something that you can do is when you have 2 methods optimizing modularity, you can always compare the values of Q that are obtained, right? Because this is your objective. The 2 methods share the same objective. And you can also compare the time that it takes in a set of empirical networks. Yeah. And indeed, that very much makes sense, but this approach clearly doesn't make sense if you try to compare modularity optimization technique with a map equation optimization technique. Because clearly, well, if you look for the value of Q, we expect that the modularity optimization will find something better because this is what it tries to optimize. So it means that this is something that can be used, but it has some limitations. Now, another way by which the people can try to validate techniques is by trying to exploit some metadata that are available for the nodes. So here on the left, you have an example where you have books that are politically oriented, where in this case the blue would be more liberal books, the red would be conservatives, and the purple would be more centrist books. What you can try to, and here you have like a network where two books are connected if they've been bought by the same person. What you could try to do is to find the communities in that graph by whichever technique you want, and then try to see if the communities that are found structurally are well aligned with the communities that are obtained from the attributes. Now, on the right, you have another example where I represent a mobile phone communication network that covers the whole country of Belgium, where each of the nodes is a community that has been found by optimizing modularity. In total, this represents about, I think, 2 million people. And the colors encode the language that the people speak, because indeed in Belgium we have 2 main official languages. That would be French and Dutch speaking. And you can see that there is a clear separation that is very well explained by the language, and there is only one community that is somehow in between languages, and that would be a small community based in Brussels, where there seems to be that within this community you really have some communication and some cohesion taking place between the two communities. Now, this looks good, right? Trying to use metadata. Now, there is a problem, and the problem now is that metadata needs not always be aligned with structure. Yeah? Or sometimes you have that several types of metadata affect the structure. You could think, for instance, about the existence of a friendship relation between people. Well, the existence of a relation between two people may be explained by the fact that they share some opinions, some political opinions, but probably that it can also be explained by other factors, right? That they have a favorite band, music band in common, also that they have some friends in common. So there are many, many factors that explain the existence of an edge between two nodes. So it means that we cannot be sure that just by looking at one metadata or two, or those that we can measure, we indeed can explain the graph structure. So it means that, again, this is something that can be done, but it needs not be always perfect. Now, a third way that people use is actually to build some versions of stochastic block models where they would decide that we have a group of nodes that forms of a community, another one, another community, and so on. So we plant a partition of communities, and then we form random connections that are constrained by these groups. And typically we have a parameter that will be such that here we basically have that we're going to be having disconnected clusters, and to the right the clusters will actually be so connected with each other that it's going to be impossible to distinguish them. What you do then is you compare the partitions that I found by the algorithm with the partitions that are found by that were planted by you in the model, and there are different numbers for that. And here is a number that is, when it's one, is that you found perfectly the solution. But typically what's happening is that there's a rapid loss of quality at some point. And what you will say is that one method is better than another one if it tends to lose its quality afterwards, right? Meaning that it can go to more random structures and yet find the underlying partition. Now, this is something that seems sensible from a statistical point of view. But again, this is a validation technique that is not perfect because it relies on the underlying assumption that graphs are random graphs. And for instance, if you were to have a method that is based, a community detection method that is based on the way triangles are organized inside the communities, well, clearly it would perform extremely poorly because in stochastic block models, as in adversarial graph, as in configuration models, the density of triangles is fairly small, and hence any method based on triangle would basically miserably fail at finding any structure. So it means that, again, we have something where we make some assumptions, and for instance, community detection methods based on stochastic block models are expected to work very well here because the validation is basically aligned with the principles on which the method is based. So this is, again, something that is important to keep in mind. And so it means that in general, when you propose a new method, and let's assume you propose a new method, the people are doing a combination of those things. Comparing, for instance, modularity with your method and other ones, trying to use some metadata and look for this alignment between the metadata and the communities that are found, and finally try to build some benchmarks and try to find back the communities that you plant with the methods and try to find them until even if the graph appears to be extremely random and where the communities appear to have been lost. Now, actually, there was a fourth method that I would like to mention, but even if it's a very difficult one to implement in practice, it was a project that was developed by a researcher that is now working for Facebook, where what he did was trying to find communities in social networks, and he did the validation by asking the people what they thought about the community of their social circles. The way to do was to construct a Facebook app where once you log in, you upload your contacts, the methods finds communities, send them back to you, and you can rate the quality of these communities. Now, this is something where you try to exploit the intimate knowledge that each of us have of our social relations. And this is, I think, a fairly promising and also very innovative way to consider the problem. The issue here being that it's very difficult to reach a large number of participants for any of these experiments. And hence, typically you can maybe run it once, but it's going to be something that is difficult to run at a large scale. Now, okay, so now I think it's time to conclude. So we've been talking about modularity, about the ways to optimize it. Now, modularity is not the only quality function, even if it's the most popular, as I said. And because it's the most popular, it's been under scrutiny, and people have been clarifying some of its limitations. And some of them are quite important, and it's important to keep them in mind, maybe to bring some improvement to Newman-Kirwan modularity. So the first problem is that it's been observed that in practical context, when you consider real-life networks, it can happen that the landscape of modularity is very rugged, in the sense that you would have partitions that would be very far from each other, meaning that they correspond to very different communities, and yet they have very similar values of modularity. But this is clearly something that doesn't look good when you do optimization. So it means that you need to be very careful, because it's not because an algorithm finds a high value of modularity and another high value of modularity that actually these partitions make sense. And in a situation like this one, maybe that we should try to represent the system not by one single community, but by an ensemble of partitions that would be all of these competing maxima that are almost similar. Now, another limitation of modularity that I think is a bit more annoying is the fact that, so initially I said that in community detection, you don't want to impose the number of clusters. You want the methods to find it itself, and ideally this number should be guided by the structure. Now the thing is that implicitly modularity tries to find communities that have a certain characteristic size. And if this characteristic size is not compatible with the underlying structure, it can then provide fairly stupid answers. So where does this dependency on the characteristic size depend? And this means that given the size of a graph, you try to find communities that have a certain size relative to the total size. Well, actually it comes from the null model. And you see that in the null model, you have a dependency on 2m, on the total number of connections in the graph. Yeah. Which means that if you have a graph that is much larger, well, you will basically have that the null model, even for the same values of ki, kj, is going to become smaller and smaller and smaller. And this will induce the fact that you will have a tendency to find larger and larger communities. Now, just an example. It's an example that is shocking when you think about it, and that really shows clearly that you need to be careful. So here what you have is a circle of cliques of size n, right? And clearly, if you want if you think in terms of clusters, the only sensible way would be to take all of these cliques as communities. And indeed, as long as you don't have too many of these cliques, this is what you're going to be finding. But if at some point you add too many of those cliques, the size of the system is going to become larger, the total number of links is going to become larger as well, and your optimal partition will now be made of pairs of cliques and not cliques themselves. So it means that certainly you provide a two-course representation of your system. You put cliques together, and this is because putting these two cliques together is at the right scale, yes, with respect to the total size of your system, even if this community is not guided by the underlying structure and actually doesn't make too much sense. So it means that you need to be careful about modularity. Sometimes when the graph is too large, it can provide communities that would be too large and could actually be combining finer structures that would appear to be intuitively much more significant. Now, there would be a last limitation of modularity, and this last limitation is the fact that when you take a random graph, adversarial for instance, and you think about what is the value of modularity of the optimal partition. So you optimize modularity for an adversarial graph, and what you can see is that actually the value of modularity increases with the size of the graph. So the larger are the graphs, the larger will be the value of Q. And even worse, you can show that for a random network, if the size goes to infinity, you will have that the modularity of the best partition actually goes to 1. And this limitation here is not annoying when you try to optimize modularity, but it's annoying because it means that you should not use modularity as a way to compare how modular different graphs are. If you have a modularity of, I don't know, like 0.5 for one graph and 0.25 for another graph, it doesn't necessarily mean that this one is more modular. And modularity should not be used as a number to compare the level of modularity of different graphs. It should be used to compare the partitions of the same graph. And that's perfectly fine if you do modularity optimization, but it shouldn't be used here in this context as a way to compare different graphs. Okay. So well, excellent. So this basically concludes this week's videos on the problem of community detection. So we've seen graph partitioning, we've seen modular optimization. Now, this is not the end of the problem of communities, because as you'll see, in the next few weeks, we'll be interested in how these communities that we've been interested in may affect the way a system works and functions. And more specifically, we'll look at the way these communities are going to be affecting dynamical processes. And in the next weeks, we'll consider the problem of how does the modularity of a graph affect dynamics and typically slows down dynamical processes. And after that, we'll see if it's possible to use the constraints induced by communities on dynamics in order to maybe build alternative quality functions, alternatives to Newman-Govan modularity, in order to uncover communities and well-defined communities in large graphs. But that will be for the next few weeks, and in the meanwhile, well, I wish you a very good week.